Hi guys, we are going to have today's class about parallel and series circuits. Well, first of all, what is a series circuit? It's something like this. This is the simplest circuit that we can imagine. It's a battery connected to a resistance, or in this case, it's a resistance that emits light. So this is resistance that we have been talking about, and when electrons flow through it, it's going to be heating up, and that heating up provokes electrons to flow through it, and then we will have some photons, which is basically light that is going to be emitted from this light bulb. So what happens when you connect the battery with the wire to the light bulb? Well, what happens, guys, is that once you connect it, you're going to have electrons flowing from one of the poles through the light bulb, through its filament, and then going back to the battery. And then this process will continue forever, or of course until this is disconnected or until the battery is exhausted. Well, that's basically a series circuit. Okay, it's pretty easy. Alrighty, now what's gonna be next? What happens if we place one of our professionals? Well, this person, he is a professional and he is connected to this battery, and we want to know how much current is going to be passing through this trained professional. Of course, he doesn't mind passing through this. He loves physics, so he's gonna be going along through this experiment. Well, he is connected right there. Don't worry, no clowns were hurt during the filming of this video, so don't panic. Alright, so we're connected to the battery. How much current is going to be flowing through this person? Well, as you can see, it's going to be the battery's voltage is 12.6 volts, which is this, and then we divide it by the resistance, which is 1000. We divide it, and it's going to be 0.0126. That is going to be the current flowing from here all the way through the person, passing through the internal organs, oh watch out, and then coming back to the battery. Now what would happen if we get another trained professional to get connected in this circuit? Well, this is what we called a series circuit. And what happens, guys? What happens when you have two of these trained clown professionals? This is going to be a resistance of 1000 ohms, and this is a resistance of 1000 ohms. So what's going to happen with the current? Well, as you can see, it's not going to be the same. Now it's going to be less because you have more resistance. So you have the same voltage, 12.6, the same as what you had before. Now we have we have more resistance, but the voltage will be staying the same. What's going to be the current? So as you can see, there's going to be more resistance because there's another resistor here, and this one is also another resistor. I'm going to show you the symbol for resistance, and it's going to be this symbol already. And what's going to be next? Well, this is the resistance of one of the clowns, 1000, and this is the resistance of the other one. So the sum of the two is going to be the full resistance that is going to be working here. So what's going to happen is that we get here less current. Now, if we continue to place more of our trained professionals, this one's 1000, another 1000, 1000, and 1000. How much current will they feel? Well, it's going to be even less because now it's going to be 12.6 divided by 4000. So evidently the current has to be lowered because you have more well, people that have resistance. You got more resistance on each of them, so the passage of the electrons is going to be hindered more than in the first case. So that's why the current now is going to be less, because now you have more resistance. Let's say that we get these two light bulbs. They are in series, just like when we had our trained professionals over here. And as you can see, the light bulb has a certain amount of light that's being emitted, right? So that means that we have current flowing through it, and that's a series circuit. Now what happens if we get more resistors? Each one of these light bulbs works as a resistor. Each of those light bulbs has a given resistance, which means that it's going to be hindering the current. Now look at the light bulb. This is what I wanted you guys to see. The light bulb has now a lower amount of light. It's emitting less light than before when you had just the two light bulbs. So what happens here is that the sum of the resistance is going to be, or the sum of each of the resistance of these light bulbs, it's going to be making the current go lower, and that would make less light being emitted from each of these light bulbs. So when you have more resistance, there's going to be less current, and that means there's going to be less light, even though you have the same voltage on both cases. So you can see the YouTube video in this channel, and you can see the full experiment and also how to build this circuit. We're going to continue then. So this is what I'm telling you guys. The resistance that we have here on each of the light bulbs, for example, this could be the clown or an actual light bulb or whatever, or a resistor, which is a device to also to be used in a circuit. And so the resistance here is going to be different on each one of them, or it could be the same, but the idea is that this is going to be exactly the same as if we would replace it with one resistor, just as we saw before. So this is one of the resistance. Let's say that this is 100 ohms, and this is also, let's say this is also 100 ohms, and this one is going to be 100 ohms. So, oh, sorry, you don't want to see that yet. Okay, so we get 100 here, 100 here, and 100 here. The sum of the three resistance is going to be resistors, it's going to be 300 ohms. So that's going to be the resistance that is equivalent to these three resistors. So that means that we can replace these three resistors for just one of these resistors. And why do we do this? Because it's going to be very useful when we solve problems, and also to understand how a circuit works. Okay, so the total effect of this circuit, it's just as if we would have one big light bulb that has the resistance of the sum of the three or the four light bulbs here. And also here the amount of light is proportional to how much resistance you would have. So if I would get a light bulb with a resistance that is equivalent to these two light bulbs, I would get the same amount of light, the same amount of current. Okay, so when you have a series circuit, all you have to do is just add the resistors, and that's what you get. Okay, now I wanted to show you a problem with the series circuit. I mean, it's pretty nifty. You can get some light bulbs to turn on, but it's very limited. And this wouldn't be very useful in your house. So let's imagine that we have this connection in your house, in one part of your house. Let's say that this is the kitchen or something like that. and over here it's the living room, and I don't know, maybe over here we have the bathroom. It's separated, whatever. Okay, so we got different parts of the house and they are connected. All the light bulbs are connected to in a series circuit. So let's say, guys, that we get our scissors, our huge scissors, and we're gonna use them to cut part of the wire. So we're gonna take that wire, we're gonna cut it down, we're gonna cut it off. And you know what's gonna happen? You see, there's no more. Uh, there's not. There's not gonna be a path here for the electrons to flow from this point to the other. So what's gonna happen? The whole house it's going to be turning off. So that will be a problem, because what if I want to turn off this part of the house? Maybe it's the living room and I don't want light right now in the living room. Maybe over here in the kitchen I do, but if I turn off one of them, the whole thing it's going to be turning off because they are connected in series. So that's going to be a big problem. Oh, he is sad now. Now we have here the other type of circuit called the parallel circuit, which is going to be avoiding such a problem, and it has also other advantages which I will be talking about in a moment. But one of those advantages is that we can disconnect one of the light bulbs and it's not going to be affecting the others. So let's say that we take again our trusty scissors and we cut part of the wire. So this is going to be cut. As you can see, the electrons can't flow here anymore. No electrons flowing here. So there's not going to be light being emitting from this light bulb. But you know what? From the other light bulbs, they still have their own path. So that means that they are going to be lit. This one's going to be lit and this one also. And this is what you need, for example, in your house. And of course, we're not going to be using scissors in your house to disconnect a wire and then you gotta connect it again with some tape. That would be very sad to do, putting some tape here. No, we don't do that. We have what we call a switch. A switch, it's like a piece of metal that when you connect it in one position, you have a connection, but when it's on the other side, there's no connection. Okay, that's, well, you know switches, right? That's what you use to turn on the lights in your house. And when it's on the other side, it's not going to be turning on. So parallel circuits come from the word for that concept in geometry. When you have parallel lines, they don't touch each other like this. But it goes beyond that, guys. It's beyond the geometry that we call it. Why we call it the parallel circuit? Because it's not going to be a parallel circuit just because it looks like parallel lines, because this line is parallel to this one, so this is parallel to this, and that's why it's parallel. No, not just because of that, but there's even more to it. So if we have a different geometrical configuration, but the electric configuration isn't a parallel circuit, it's still a parallel circuit. But we're gonna get into that a little while later. Okay, so the parallel circuit, it's what you're going to be using in your house. Everything in the house, the lights, the these plugs for your televisions and refrigerators and so on, they're all connected inside your house through a parallel circuit. So if this thing is cut off, or maybe this thing is cut off, all the other circuits are going to be surviving. And that's why we have the parallel circuit. Okay, but that's not it, guys. Now I went into this website and it's pretty cool. You can do a lot of pretty crazy circuits. It has a battery, get the fuse that I told you about back in the other class. You can do a lot of things. It also has a dog. I don't know why there's a dog, but I guess you can do some circuits there with dogs. I don't know. I tried doing it, but it didn't work. Connected the dollar. Oh, you know why it didn't work? Because I placed a dollar. That dollar That thing has a lot of resistance. That thing, that's why it cut off my electrons flowing through there. And maybe that dog has a lot of resistance. I don't know what happened, but I did do this circuit over here, which I want you to see it, guys. So I did this circuit with a battery of 9 volts, and as you can see, I placed the voltage meter, or the multimeter. It's just a voltage meter, and it measured 9 volts. And okay, let me play that again. So I measured the voltage in each parts of the lamp, and they all have the same voltage. So the moral of the story here, it's that when you have a parallel circuit, they all have the same voltage. And we will be talking about that in a later video. But just hold on to that thought for a while. Right now, when you have parallel circuits, the voltages are gonna be the same. Now here's the other video that I wanted to show you. I placed the ampere meter, which is the one that measures current, and I measured the current passing through this simulated circuit, and as you can see, I got here 0.43, and over here it's 0.43, and over here we got 0.86. What do you know? What a coincidence, or is it? What does it mean? So we had 0.86 here, which means that this is the same as the current passing through here and the same current passing through here. When you add those two currents, you get 0.86, because that means that the current that's passing through the battery, it's going to be supplying each of the branches in this parallel circuit. So this part of the circuit is going to have 0.43 and also 0.43, because both of them have the same resistance. They're the same light bulb, and as you can see here, what I'm saying, guys, is that the current passing through here, it's going to be distributed into these two branches. Okay, let's do this other part. Now I want to show you here the resistance for the light bulb. It's 21 ohms, and then the resistance here, it's going to be also 21 ohms. And how do we use this? Well, I'm going to do the circuit, the same fun circuit. I'm going to place it over here, but now as a electrical diagram. So this is the symbol for the battery. Why is it like that? Because the original battery that was made by Alessandro Volta back then in the 1700s, a while ago, it was made by piles of salt and paper and a pile of nickel or some material like that, and another pile of more salt with paper, and then some nickel and metals, like that, and then a pile of paper and so on with the salt, and so on and so on. And he had like a big sandwich of nickels and salty paper with water. And that's how he made the first battery. And you guys can also do that experiment if you want. Probably you have done that already with nickels and putting paper with water and salt and so on. Anyways, the idea, guys, is that this symbol represents any battery. It represents this battery or the battery that I showed you in the beginning with this one over here. Or it can also represent the voltage that you get from CFE, from the plugs from your house. That's going to be 9 volts. Alrighty then. Well, as we said, the voltage is going to be the same here, here, and over here. So the voltage, when you have a parallel connection, it's going to be exactly the same. So that means that I can get the current with my formula for, remember that formula for voltage equals resistance times current. That is the Ohm's law. And with this we can get the current. So when we clear for intensity or current, it's going to be voltage over resistance. And that's what I did right here. So we got 9 volts on the resistance that we have right here. So we got 9 volts over 21, that's going to be 0.43. And then we have 9 volts over 21, that's going to be 0.43 as well. And that's the current that we have here. Now we have a current, and we measured a current over here of 0.86, right? And it makes perfect sense because when you add 0.43 plus 0.43, it's the same as 0.86. Okay, so this is going to be the big idea, guys, that I want to show you now. The big idea is that this circuit could be easily replaced by this other circuit where you have one resistance where it's not going to be 21, but now it's going to be 10.5. So with this 10.5 resistance, if we divide the voltage, 9 volts over 10.5, it's going to be 0.86. This would have a current of 0.86, so this would be also 0.86. So this circuit and this circuit, for the battery, from the perspective of this battery, this is an eye, here's another eye, it's supposed to be an eye. Also over here we got some eyelashes on that eye. From the perspective of this battery, this circuit and this circuit are exactly the same because the battery is giving away 9 volts and it's giving away also a current of 0.86. So that means that this circuit could be easily replaced by just one resistance. And this also means that even if we have a more complicated circuit, something like this, or more things, more complicated things, a circuit that would be used, for example, to represent a television set could easily be replaced by one resistance in order to be analyzed. So that's what I'm talking about. I'm talking about equivalent resistance. Now, the resistance here used to be 21 and 21, but now it became 10.5. What is the relationship between these numbers? Well, 10.5 is the half of 21. Alrighty? Now let's look at this, guys. Let's look at this circuit. Now I placed there a a resistance of 10.5, and the voltage, of course, is going to be the same. It's the same battery. Now I placed the current there, and it's going to be 0.86 amperes. And as you can see, the resistance, okay, I'm going to check the resistance. Let's check it out. There you go. It's 10.5. That resistance, it's what I was telling you about. It's 10.5, and over here it used to be 21. This one was 21. There you go. And it gave us the same current flowing through this part of the circuit, through the battery. So this one, this circuit and this circuit are exactly the same. They are equivalent circuits. So what's going to be the generalized idea for this circuit, guys? What do we do? Well, when you have two resistors that are placed in parallel, like this R1 and this R2, they are in parallel, as you can see. The equivalent circuit is going to be one resistor that its value will be calculated through this formula or this formula or one of these formulas as well. Okay, it's basically doing this. It's going to be 1 over R1 plus 1 over R2, which means that you have to get the reciprocals, that is the number that you place under the denominator or as a denominator. So the reciprocal of 21, it's 1 over 21, and after you add them, you gotta get the reciprocal of that, and if you do that, it's going to be 10.5. And here's a shortcut that you can follow in your calculator, that you can do in your calculator. It's going to be easier than doing this because in your calculator there's going to be a key that says x to the power of -1. So that key, it's going to be basically the same as putting in the calculator 1 and then division symbol and then your number, for example 21 or whatever. And you can skip all of that by just doing 21 and then hitting this key. It's going to be equivalent to doing 1 over 21, but that's just a little shortcut for you guys to do after you understand what's going on here, and also to make things a little bit faster. So the resistance, the equivalent resistance, is going to be 1 over the reciprocals of each of the resistors. And when you do this, guys, it's going to give us the half of what you have. It's going to be the half. Okay? And there's also another formula that if you multiply the denominators and then you simplify this for two resistors, you're going to have this formula. And if you want to use this formula when you have only two resistors, maybe it's going to be faster than using this other formula. But it's up to you. Maybe you can use this one for mental calculations, which is basically just multiplying the two resistors and then dividing by the sum of those two resistors. And it's going to be also the same as this one, or as this one, or as this one. But this only works when you have two resistors. This one is going to be for more. As in this example, we have here four resistors. They are placed in parallel, and we want to calculate the resistance that is equivalent for this circuit. So what's going to be that one resistance that represents this circuit? How much is that going to be? Well, I've got to calculate the reciprocals of each of these guys, which means that I'm going to take this number, for example, and then I'm going to place it under the 1. So it's going to be 1 over 10, which is this guy, plus 1 over 20, which is this other guy, 1 over 20, plus 1 over 30, and plus 1 over 40. That's what I have right there. And after you do that, if you want to do it manually, you can do the operation right there. Then you do this operation, you get the number, and then you do 1 over the result of this thing. Or you can do it completely directly on your calculator as 1 divided by parentheses. You can do this in the calculator like this: 1 divided by parentheses 1 divided by 10 plus 1 divided by 20, and so on and so on and so on until you reach 1 over 40, and then you of course got to put the parentheses. Or you can use, of course, the reciprocals. You got to do the reciprocal of each of the numbers, you add them, and then that result you got to do the reciprocal of that as well. If you plug this into your calculator, it's gonna be understanding it. Of course, you got to remember that you don't put exponent to the -1. No. Avoid that. That's not the whole point of the shortcut. The shortcut is that in the calculator, there's already a key for the reciprocal, which is x to the power of -1. You got to look it up. It's right there. It's very useful, guys. All right. So this means that this big circuit, this huge circuit, all of this can be replaced by just one of these resistors, which is going to have a value of 4.8. So for the perspective of this voltage source, this huge resistor, this huge circuit with these resistors, it's going to be equivalent to just this one. So that's why it could be replaced by this, guys. Alrighty, that's the whole point of this. Now this, guys, what's gonna happen here? How do we get the equivalent resistance for this circuit? Now, is this in parallel, or is it in series, or is it in series? Well, maybe it may look like a little weird because it's not like this. But as I was saying a while ago, even though the geometry is not in series or in parallel, electrically it is in series or in parallel. And in this case, this is a series connection, because when it's a series connection, there's only one connection between the elements. So between this element and this element, there's just one connection. If there would have been something else over here, that would stop making it a series connection. But if you just have one element connected to the other element and there's nothing else in between, that is a series connection. So this and this guy, they're connected in series, and this guy with this guy, they're connected in series. Imagine that we have, if it would help, imagine that we have here the clown or a person, and he is holding hands with the other person over here. That hand is on his head. Don't mind that. I want to put another hand over here, and here's somebody else, and they are holding hands like that. So that makes it a series resistor. So what do you do, guys? How do you solve this problem? Well, you gotta add all the resistors. You gotta add this resistance with this resistance and this resistance because it's in series. So that's all you have to do. The resistance has to be increased. That's what happens when you have a series connection. So you add. But if it would have been in parallel, you need to do all of this procedure. Alrighty, so that's gonna be it for this one, and I just wanted you to let you know that this is going to be very useful in order to understand circuits, and also when somebody is fixing a computer or some device, and let's say that they don't have one of these resistors, or let's say that they need to get, let's say they need one resistor, and the technician could look for that resistor, or he could make his own resistor by combining some other two circuits, some other two resistors to get that desired resistance. And that's also like something useful about equivalent resistance circuits. And of course, it's also going to be useful to understand how computers work, how electronics works, and it's going to be very important in order to make these devices, guys. So that's going to be the reason why we study equivalent circuits. Alrighty, guys, so what I'm saying is that this computer could be represented by just one big resistor, and electrically it's going to be the same, and this could simplify a lot of analysis and operations and so on. But that's going to be only at the circuit level or the electrical level. Anyways, guys, that's it. You have a great day. I'll see you later.